Welcome to Artificial Intelligence Foundation and Application course. Today we'll be looking into the second part of the reasoning under uncertainty or the probabilistic reasoning. So in the last lecture we have seen how we can model a system, and given a belief network, how we can identify the probabilities, the conditional probabilities, then some kind of conditional independence. We have looked into that stuff. We will look more into that part today as well. So just to start with, like in the last lecture we have seen given the belief network, and we can find out the probabilities. That's the stuff that we looked into in the last lecture. Today we'll be looking into that how we can actually form a belief network, and what would be a good way to form that belief network, and what are the pros and cons and all those stuff. So let us take this example. Like say I want to model the traffic and the relation with rain. So consider this situation like we have the following two variables, like R, it is raining, and T is there is a traffic. So these two are the things given to me. So there are various ways I can actually model this problem. So let us look into how we can do that stuff. So it's very easy to understand that if there is a rain, then there is a traffic. So we can construct, we can have these two variables, rain and the traffic, and the relation between will be something like rain to traffic. Now if you want to describe the probability table, then I just need to specify what is the probability of rain, and we need to specify the conditional probability for what is the probability of traffic given that it's a rain, and what is the probability of traffic that is under the condition no rain. So some value we have to provide and from there we can actually find out the joint probability. So which will be something like when it is raining and there is a traffic, when it is raining and not traffic, and all sorts of stuff we can actually construct from these two tables. So, and in order to find out these tables, particularly this one and this one, we can observe a lot of scenarios. Based on that we can actually construct the table, like what is the probability of rain we can observe, and if you look for several days and when there is a rain and there is a traffic, we can find out this probability table. And finally we can combine these two to get this joint probability stuff. And based on that we can also compute the probability of traffic will be kind of 9 by 16, that we can actually figure it out. Now let us consider the situation which we call reverse traffic. So it is the same scenario, we'll be using the same set of variables, but we model it in this way. So when I say traffic influences the rain, so which is unlikely, but let us proceed in this manner and then see what happens actually. So probability of traffic is 9 by 16, that we know, so that is given. Then probability of rain given traffic that we observe, let's say it comes out to be this table. Okay, now so once we have these two, we can actually find out the joint probability distribution. And interesting thing is that this joint distribution will be the same as the previous joint distribution that we can show you. So it is the same one. So the thing is, whatever we model, the joint probability will remain the same, because that is the most fundamental stuff, and then we are just modeling the dependency part, so something can get varied, or all those things we have to just explore which is dependent on what. But the thing is, joint probability will remain the same because it is the underlying whole stuff. Now, one interesting thing to note here, earlier we used to find probability of traffic given rain, and now we are determining probability of rain given traffic. Now, finding out this probability is easy. When I know rain or no rain, I can find out whether there is a traffic or not. But the problem is, if I observe traffic having rain and no rain, that is the difficult part. So therefore, if I try to determine this probability table, it will be difficult to obtain. But when I try to find out this one, this is relatively easy for me to figure out that probability, conditional probability table. Now, in practical scenario, there are, in many cases, if we model it in any way, probably will be representing the correct same thing. But if we represent the dependency in proper manner, that can help me in determining the conditional probability table, and that can help in further computation. So we have to take care of that stuff. Now let us look into another example. So here, when we try to solve a problem through belief network, so given a network and we can reason about certain probabilities, and this belief network can be very complex. There will be a lot of dependencies kind of stuff. So let us first construct such a table, and then see what are the issues and how we can actually proceed further. Now, so let us see the problem first. So the problem says there is some chance that tomorrow will be cloudy, and if it is cloudy, then chances of rain is high. Also, there is a sprinkler to water the grass. When there is a prediction of cloud, it is likely to run sprinkler. We want to model whether grass is wet or not. So first thing is, we need to find out the variables. So definitely cloudy will be one of my such variable, and then having rain is another variable, and I can run the sprinkler. And finally that we have to check whether the grass is wet or not. So these four are the primary events that we need to model. So let us proceed. So the thing is, let's say cloudy, sprinkler, rain, and the wet grass. So these four are my variables. Now you have to find out the dependency between this set of variables. So definitely, if it is cloudy, I may not run the sprinkler. If it is cloudy, then it can be high chance that it will rain. And whenever the sprinkler or the rain if you turn on sprinkler or if the rain happens, then the grass will be wet. So this is the actual scenario, and then we have to provide the probability values. So cloudy is independent, I can provide the probability, and then we have to provide the conditional probability for sprinkler and the rain, and we have to specify the probability for wet grass. So this is actually probability of wet grass given S and R, because this is the actual dependency. So I just implicitly removed S and R because we have given this one under the different scenarios. So the thing is, now if I want to reason what is the probability it is wet grass, then I have to go to this path, I have to go to this path as well. So, and there can be a situation that there will be some other kind of stuff here lying above a pit. Now it may happen that when I try to move along this graph, I may keep on visiting the same node multiple times. Now if I keep on visiting the same node multiple times, then that can be a computation issue, because so I want to compute probability along this path, then I just check the probability of cloudy and then we compute further, similarly for the rain and so on. Then sometimes it becomes difficult to manage. So what we can do, we can actually merge some of the nodes. In that case, if I can merge these nodes, then there will be only one edge here and there will be another edge here. So effectively, if I want to find out what is the probability of wet grass, I do not move to cloudy twice. I can simply go through this path and actually I can find that stuff out. So let us see how we can actually proceed for that one. And if this is given, then you can actually find out the probability, joint probability, so which I'm not going to explain much, and you can actually figure this stuff out. Now now the thing is, if you look into the previous one, then you have to reach to cloudy part in multiple ways. So cloudy will depend, the cloudy will control some of the variables in your belief network. Now when I make the graph in this way, so cloudy, sprinkler plus rain and the wet grass, then if I make my graph in this way, I can analyze pretty easily. And interesting thing is that if I want to find out wet grass, I just need to know the sprinkler and rain, and then I can actually figure that thing out. Because if some information is given about sprinkler and rain, then I just do not need to know about the probability of the cloudy. I can or if I need to know, but that will be with respect to sprinkler rain to cloudy. So I just do not need to know with respect to wet grass to cloudy. So I can segregate that stuff. And my computation will be reduced. But now the thing is, I have to provide a different conditional probability table. For this case, I have to provide the conditional probability for the cloudy is this one, so which will remain the same. Sprinkler and the rain, this was the value that we have from the previous stuff, and this was the probability values that we have already seen for the wet grass in the previous one. Now if I want to compute the new one, then only this part will get changed, only this set of values will be changed. So I need to provide a different table for this one, and I have to provide these probability values. This is actually given C. So how we can actually compute that stuff? So in order to compute that one, I need to use the previous tables. So let's say I want to compute something like this. When S and R both are true, and it is given that my C is also true. Now if C is true, then the probability of having S to be true is 0.1, and when C is true and probability of R is also true is 0.8. So effectively I will get 0.08, because these two are conditionally independent, and we know So effectively I know, so this is S, we are trying to find out S and R given C, and since S and R are independent given C, so it will be P of S given C times P of R given C, and we can actually compute that value. Now similarly the other values can be computed in the same manner. Now when I have something as F, then I need to consider 1 minus that value, and I can actually figure that thing out. So by doing this, it will help me in reducing the number of nodes that I need to visit, because I will be merging these two nodes, so I can simply move through only along a single path. And if the graph is complicated and there are a lot of dependencies, and if we do not merge, then that can lead to some kind of a computational issues. So let us take a problem and let's try to model the problem on this one. So you'd like to build a belief network for the following. Let us assume that you are interested in pursuing PhD at IIT KGP. To take admission in PhD program, you may need to provide at least 2 recommendation letters from the course instructors or to appear Prime Minister Research Fellow interview. So I will try to model simultaneously as well, or I will try to mark the variables as well. So one of the variable is I'm interested in doing PhD or not, and I need 2 recommendation letter. So let me call this R1 or 2, and let me call this as PhD, and or I need to appear for PMRF interview. So that is my another variable. A course instructor can provide at most 1 recommendation letter based on your grade on the subject. So I need 2 recommendation letters, so it will be effectively linked to 2 grades. So let me call this as G1, G2. So the course instructor can provide at most 1 recommendation letter based on the grade that you have got on the subject, and this grade depends on attendance. Let me call this as A1 and A2, assuming you have 2 different attendance in 2 different subjects. Marks obtained in the assignments, so let me call this as AS1 and AS2. That is the marks, this is AS2, and the marks in the assignments and in the final examination. So let me call this as F1 and F2. Now intelligence of the student can also play a major role in the performance of a subject or in interview. So definitely this is one of the variables, so let me call this as I, that can affect the performance of a subject. So effectively this can be the performance in the assignments, or it can be in the final examination, and interview is there, PMRF, so that can also be influenced. You may feel happy if you perform well in the subjects or you get admission for the PhD program. So another variable, let's say whether I am happy or not, that will depend on how I am performing on the different subjects and whether I am getting into the PhD program or not. So now in order to model this environment, we can proceed in the following manner. There can be many ways you can model, so this is just one such model. So first thing is that we to to get into PhD we need recommendation letter. Recommendation letter will depend on the grade. So I can say I have grade G1, I have grade G2, and this will depend on the recommendation letter R1 or 2, and grade will depend on my attendance A1, my assignment marks, and the final examination marks. Fine. Similarly for this one it will be A2, it will depend on the assignment marks AS2 and the final grade. Okay. Now I will have the selection in PhD. So I have a PhD and I can appear for PMRF interview as well. Okay, and I can feel happy if certain things happens, and there will be some kind of a intelligence which will control certain things. Now if I try to depict the dependency, then intelligence will depend my performance in the assignment. Intelligence also influence the marks in the final examination. So this will depend, this will influence these two as well, and intelligence will also influence how my interview is happening. So I can write in this way. So there will be one edge going to here, and the grade is related to the final marks, the assignment marks, and the attendance. Similarly from here it will depend on this, it will depend on this, and it will depend on this. Grade 1 will have a probability that I'm getting a recommendation letter. Similarly for grade 2 will have influence on the recommendation letter 2, and all of this will have dependency on the PhD. So if I receive 2 recommendation letter, I'll be through, or I have to appear for PMRF. And I feel actually happy if I get admission in the PhD program, or I perform well in the subject. So the grades will have some impact on my happiness level. So this will be one such belief network, and if we know these probability values, we can actually find out we can reason about the probability values for different scenarios. So moving forward, like when we try to model a problem, then what we do, we use an approach known as incremental network construction. So we select the set of random variables to describe the domains, which will be the very first step.